Okay, so welcome to all of you. Today we will see the next chapter, that is chapter 2, divisibility theory in the integer. So you know that the set of the integer is nothing but set of the integer is what? 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on. This is the set of the integers. Okay, so our whole chapter is focused on this set. This is the set of the integers. Whole chapter is focused on the set of the integers. Okay, so now then the mathematical induction. You are familiar with the mathematical induction in the 11th standard. So we'll see some examples of that mathematical induction also. So before that we will see what do you mean by well ordering principle. So every non-empty set S of the set of the natural number, that means what, if you want to say in terms of the integer, set of the natural number means what, the set of the positive integer. Set of the positive integer means what, 1 2 3. Note that 0 is not positive. 0 is neither positive nor negative, right? So if you are saying that what, the positive integers, the positive integers are 1 2 3. The set of the natural number is nothing but the set of the positive integers. Okay, so now if S is the set of the positive integers, that means S is the non-empty subset of S is the non-empty, every non-empty set S of n contains a list element. That means what, every subset of a natural number having a list element, having the smallest element. Okay, that is the well ordering principle. Okay, so now the first principle of the finite induction is that S is a subset of n, that means the set of the positive integers, with the following property. The integer 1 is there, so if k is there, then k plus 1 is also there, then S is equal to n. That means the set of this S, it is the subset. We have seen that it is the subset of the natural number, but if it holds these two properties, then your S is the same as the set of the natural number. Okay, so now how to apply the mathematical induction while solving the problem. Okay, so how to solve the problem by using the mathematical, this theorem. Okay, so I am not proving this theorem, so just we are explaining this theorem now. Okay, so now how to solve, how to apply the mathematical induction while solving the problem. So your step one, what, let Pn denote the statement. Pn denote the statement. Okay, Pn denote the statement. You know that in the last year you have seen that statement is what, an assertive sentence which is either true or false but not both. It's called a statement, that you know. So call that statement as Pn then. Okay, you know how to denote the statement is what, Pn like this. A is what, Ram is tall. So what, mathematics is easy. R x square plus 1, x square plus 1 is less than 0, something like this. These are the statements, suppose. Okay, so you know how to denote a statement and so on. Okay, step 2, verify the result that for n is equal to 1. Okay, now step 3 what, assume that pk is true, that means your result is true for some k belongs to n. Okay, so if you want to prove anything with the help of the set of the natural number, so then you can apply the mathematical induction. If your n is n is natural number, then only you can apply the mathematical induction. We will see in the problem. Now step 4, prove that pk plus 1 is true. So if you prove this, right, up to 4 steps, then your mathematical, this is the first principle of mathematical, or you may say that what, by mathematical induction result is true, then Pn is true for all n belong to n. Okay, so these are the 4 steps, right? If you follow these 4 steps, then the problem will be very easy. So we'll do the problem so that you will understand how to apply these 4 steps while solving the problem. Okay, show that show that 1 square plus 2 square plus dot 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 plus n square is equal to n into n plus 1 into twice n plus 1 upon 6 for all n belong to n. For all n belong to n. Now see, your result is depend on the set of the natural number, right? So if the result is depend on the set of the natural number, try to apply the mathematical induction. Okay, solution. We will apply mathematical induction on n. Okay, so step 1. What step 1 is what you have? Pn denote the statement. So let Pn denote the statement. Pn. Okay. So step 2. For n is equal to 1. Okay. Your LHS. One. This is what the sum of first n terms. The sum of the squares of the first n terms. Your n is 1. So then this is what? 1 square. Your LHS is 1. So this is 1. What is your RHS? You have to put n is equal to 1 here. So this is what? 1 into 2. So twice n plus 1 means n is equal to 1. Then this is what? 2 plus 1. So this is 3 upon 6. This is 1. Right? So for n is equal to 1, LHS is equal to RHS. Right? So therefore P1 is true. P1 is true. Okay. So your step 2 is over. Your step 1 is very easy. Now we'll go to the step 3. Okay. So step 3. Assume that Pk is true. For some k belong to n. So that is 1 square plus 2 square plus dot 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 plus k square. Your n is equal to k. So this is what? K into k plus 1 twice k plus 1 upon 6. We call this as 1. Okay. So for all. Now step 4. This is very important step. Step 4. We want to prove Pk plus 1 is true. This we want to prove. This 4th step is very important, but without step 3 we cannot do the step 4. We want to prove Pk plus 1 is true. That is to prove that here what we have to put n is equal to k now. Okay, that is why to prove 1 plus 2 square dot dot dot. This is what? K plus 1 square is equal to. Replace k as n as k plus 1. So this is what? K plus 1. N is equal to k plus 1. This is then what? K plus 2. Then this is what? N is equal to k plus 1. So twice k plus 2. That means this is what? Twice k plus 3 will be there then. Upon 6. This we want to prove. Okay. So we'll take the LHS. So your LHS is equal to what? 1 square plus 2 square plus dot dot dot. The k square is there. This is what? This term is are increased by 1. What is the previous term of k plus 1 square? Is the k square plus k plus 1 square. Right? By step 3, you have the step sum of this first k terms. Right? You have this. So what is that? That is what? K plus 1 twice k plus 1 upon 6 plus k plus 1 square. Okay. Now we take the addition. So we take k plus 1 common and we will do the addition. K plus 1 common. What is this? This is what? 2k square plus k. Right? So 1k is there. That means what here? 6k plus 6 upon 6. Here I have taken k plus 1 common. What we get then? K twice k plus 1 upon 6. I have multiplied by this to k. So this is what 2k square plus plus k upon 6 is there, but here only k plus 1. You have to multiply by 6 to this k plus 1. So this is what k 6k plus 6. That means what, if this is of the form C, then what we have to do, a plus bc upon c, right? A plus bc upon c. Just I have did this, right? I multiply by this 6 to the that c. Your c is what, k plus 1. Okay, so this is what, then I do the calculations here. K plus 1 into, what is this, 2k square will be as it is, 2k square will be as it is. Okay, so this is what, then this is what, then 7k square. Okay, so plus 7k square plus 6 upon 6 upon 6. So you have to factorize this. You have to factorize this. So what was the factor of this one? Factor of this one, right? So see, so this is what, k plus 1, k plus 1. Factor of this one, product is what, 12. So we will factorize this here now. Okay, so I will take the space for this one, plus 7k square plus 6. How you can factorize this one? 2k square. Your product is what, 12. So 12 means what? So how can I write this? Product is 12 and the sum is 7. So the numbers are 4 and 3, right? So I can write this is what, 4k, not this is 4k plus 3k plus 6, right? So I can write this. I will take the twice k common here. So if I take the twice k common, I get k plus 2 here. I will take 3 common here, k plus 2 there, right? So this is what, twice k plus 3, k plus 2 here. Okay. So now this is what, k plus 2, k plus 2, twice k plus 3 upon 6. Upon 6. Now see, what do you want? You want to prove that k plus 1, k plus 2, twice k plus 3. K plus 1, k plus 2, twice k plus 3 upon 6. You get this, right? So therefore, pk plus 1 is 2. So therefore, pk plus 1 is true. Hence, by the principle of mathematical induction, Pn is true for all n belong to n. Okay, so we have proved this. The problem is over here. Very simple problem. You have seen in the 11. Okay, so we'll do one more problem. For n greater than 1. Next problem. Okay, for n greater than 1. Prove by mathematical induction. Actually, the command is here. Mathematical induction that 1 plus 2 raised to 1, 2 raised to 2 dot plus 2 raised to n minus 1 is equal to 2 raised to n minus 1. Okay, so n greater than 1. So your n is natural number. For n, so the command is given mathematical induction, that means n is a natural number. Okay, so we'll prove this one. Okay, solution. So here already command is given mathematical induction, so no need to say that we will apply the mathematical induction on n, because what, the command is there directly. So with the help of the mathematical induction, we have to solve the problem. So we directly go to the step 1 here. Step 1. Let P and denote the statement. Okay, P and denote the statement. Your n is what? n belong to n. Okay, so this is your natural. Okay, step 2, step second, for n is equal to 1. So we'll take the LHS. LHS is 1. That means what? This is the sum of n term. This is what? 1, 2, 3 up to n minus 1. And this is 2 to the power actually 0 here. 0, 1 to n minus 1. So this is sum of n terms. So that means n is equal to 1. That means sum of the first 1 terms. So that is what? N is equal to 1. Your LHS is also 1. What about your RHS then? Your RHS. What? 2 raised to 1 minus 1. 2 raised to 1 is 2. Minus 1 is 1 again. Right? So therefore what? LHS is equal to RHS. So therefore what? P1 is true. So the result is verified for n is equal to 1. Okay. So now next, step 3 is what? Step 3. Step 4 is actually very important. Step 3. Assume that Pk is true. Pk is true. Pk is true for some k belong to n. Okay. So that is 1 plus 2 raised to 1, 2 raised to 2 plus 2 raised to k minus 1 is equal to 2 raised to k minus 1. This is true. Okay. Step 4. This is very important. Step 4. We want to prove that Pk plus 1 is true. Pk plus 1 is true. That is to prove that. What we did here, replace n by k here. We did the step 3 now. So for step 4, we have to replace n as k now. So what is that? That is to prove that 1 plus 2 raised to 1, 2 raised to 2, dot dot dot, 2 raised to, we have to replace n as k plus 1. So k plus 1 minus 1 is what? 2 raised to k. So this is what? 2 raised to k plus 1 minus 1. Okay, this we want to prove. We'll take LHS now. We'll take LHS. 1 plus 2 raised to 1, 2 raised to 2 plus dot dot dot. So this is 2 raised to k is last term. Take the previous term also. So the previous term is what? This all the powers are increased by 1 1 1. So previous term is what then? 2 raised to k minus 1 plus 2 raised to k, because we have to apply the step 3. Without the step 3, you cannot do the step 4. So you must have to apply the step 3. So this is the step 3. The position of the step 3 we did here. Okay. So you know that this sum with the help of the step 3. This is what? 1 plus 2. This is what? 2 raised to k minus 1 plus 2 raised to k. Right? So what is this? 2 raised to a plus a is what? Twice a. A plus a twice a. So 2 into 2 raised to k minus 1. Right? But 2 raised to 1. So this is what? 2 into 2 raised to 1. So this is the product. Base is same. And we are taking the power of this. What? This is 2 is there. That means this is 2 raised to 1 is there. Right? So that means what this is? 2k plus 1 minus 1. Right? And that we want. This is what? 2 raised to k plus 1 minus 1. And we have proved this 2 raised to k plus 1 minus 1. So therefore what here? Pk plus 1 is true. Therefore Pk plus 1 is true. Therefore by the principle of, write the principle, spelling of the principle PLE, and our college principle PAL. Okay. So by principle of mathematical induction, the spelling of the mathematical induction is given in the problem. Okay. So by the principle of mathematical induction, Pn is true. Pn is true for all n belongs to n. Okay. So now your problem is over. So what here? The step 4 is very important. If you do the step 4, then the problem becomes very easy. Okay. So I hope that you understand this, how to prove the problems with the help of the mathematical induction. Look, we will do one more problem on the mathematical induction. For n greater than 1, prove that 1 upon 1 square plus 1 upon 2 square plus dot 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 plus 1 upon n square less than 2 minus 1 by n. Okay, so n is what? Natural number actually. Okay, so here what the command is not given, right? So we'll apply. So solution. So solution. We will apply. We will right now. We will say here. We will apply. We will apply mathematical induction. Induction on n. So step 1. So step 1. Let Pn denote the statement. Okay. So your n is natural number. Your n is natural number. Okay. Now step 2. This is very simple. What? You put n is equal to 1. Okay. So your LHS. Your LHS. What? This is the sum of first n terms. See here 1, 2 up to n. That will be these are the n terms. Okay. So your LHS is what then? 1 upon 1 square. Only single term. That is 1 now. What is your RHS then? What is your RHS? RHS is what? 2 minus 1 upon 1. So this is what? 1. So this is less than or equal to. Right? So that means what here? LHS is less than or equal to n. No? So this is true. Therefore what? So this is no, you don't say LHS equal to RHS. Okay? So P1 is true. P1 is true. So just say it less than or equal to. Okay? Because what? If strictly less than, then P1 is not true. Because 1 is less than 1, this is not true. So there should be less than or equal to. Okay? So we'll do the correction. Now step 3 now. This is very important. Okay? Step 3. Assume that Pk is true. Pk is true for some k belongs to n. N is the set of the natural number. Okay, so that is we are assuming this is what 1 square, 2 square. That is what sum of the up to the k terms. It is true. Dot 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 plus 1 upon k square 2 minus 1 upon k. We have this. Okay, step 4. Step 4. We want to prove Pk plus 1 is true. Is true. That is to prove that. What? So you have to this replace n as k plus 1. So 1 square plus 1 upon 2 square dot 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 1 upon k plus 1. This is what? K plus 1 square less than equal to 2 minus 1 upon k plus 1. This we want to prove. Okay? So we prove this one. We have to prove this one. We have, just put right. We have what? This we have 1 upon 1 square by step 3. Okay? So this is 2 up to k 1 upon k square. Okay? 1 upon k square less than or equal to 2 minus 1 upon k. What we will do? We'll add 1 upon k plus 1 square in the both. Okay, so this is what 1 upon 1 square, 1 upon 2 square, dot 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 plus 1 upon k square plus 1 upon k plus 1 bracket square less than or equal to 2 minus 1 upon k plus 1 upon k plus 1 square. Right? We have adding 1 upon because it is whatever is adding. If you add any whatever this positive or negative term in the inequality, this is inequality, then inequality remains as it is. Okay, no problem for the inequality. So then this we want to do. Okay, this we have to prove. Okay, we'll keep this as it is now. Okay, now we'll simplify this now. 1 upon 1 square, 1 upon 2 square plus dot dot dot. Now no need to write 1 upon k square. We'll directly write this one 1 upon k plus 1 square less than equal to. Okay, so 2 minus I'll take minus sign common. Okay, then 1 upon k minus 1 upon k plus 1 square. K plus 1 square. So this is less than or equal to. Okay, we have to write all those things. Okay, so here we have to prove that this is 1 upon k plus 1. Okay, so we'll cross multiply this. So this is what k square plus twice k plus 1. Okay, so if you cross multiply minus k now, minus k upon k plus 1 square, upon k plus 1 square. So your k get cancelled. So this is 2 minus k square plus k plus 1 upon k plus 1 square, upon k plus 1 square. Okay, so this is equal to again your k is here now, your k is here. Okay, so k square plus k so here you have to put k. Okay, this is what, this is less than or equal to, no problem for this k. So this 1 you can remove this k 1 because what inequality is there. So I can write this is what k square plus k upon k into k plus 1. So if you draw this one bracket square, okay, I can remove this one because what less than or equal to. That is what here, if 3 is less than 4, I can write 3 is less than 5 also. Because what 3 is already less than 4, I can write 3 less than 5 here. Okay, so this I can do here. I can remove this one also. Okay, because this term is also biggest one. Okay, so then this is what 2 minus. So this is what you have. You if you take the k common, so k into k plus 1. So k into k plus 1 cancel. So this is 1 upon k plus 1. I can remove this one because what this is less than or equal to. Okay, so no problem for less than or equal to. Okay. So this is what here, then this you want, therefore what pk plus 1 is true. Therefore the principle of by the principle of mathematical induction Pn is true, for all n belong to n. So the problem is over. Okay. Next problem, prove that 8 raised to n minus 3 raised to n is an integral multiple of 5 for all integers greater than, for all integers n greater than equal to 1. All integers n greater than equal to 1 means what? N is the natural number. Okay, solution. Let Pn denote the statement. Okay, so solution step 1. Actually, I have to say this is what. So we'll apply the mathematical induction. Okay, step 1. Let Pn denote the statement. What? 8 raised to n minus 3 raised to n is an integral multiple of 5. Integral multiple of 5 means what? 5 times some n, where n is the 5 times some k now. Okay? It is a natural number. Okay. k is the integer now. Integral multiple of 5 for all n, belong to n. Okay, so no problem. For if you say n greater than equal to 1 means n is a natural number. You may say for all n greater than equal, for all n belong to n. Okay. Okay, so step 2 now. For n is equal to 1, for n is equal to 1, for n is equal to 1, 8 to the power 1 minus 3 to the power 1 is equal to 5, right? Is multiple of is an integral multiple of 5, because what, this 5 is nothing but 5 into 1 and 1 is the integral, so 5 will be multiple of 5, no problem for us. But therefore P1 is true, so your P1 is true. Okay, now step third. Okay, assume that PK is true. For some k belongs to n. For some k belongs to n. That is 8 raised to k minus 3 raised to k is an integral multiple of 5. That is 8 raised to k minus 3 raised to k 5 times m belongs to z. This is very important. M belongs to z. You must have to write this m belongs to z. Okay. Now step 4. This is very important now. Step 4. We want to prove Pk plus 1 is true. That is to prove that 8 raised to k plus 1 minus 3 raised to k plus 1 is an integral multiple of 5. This we want to prove. Okay, so we have this 8 raised to k minus 3 raised to k is integral multiple of 5. So we write this is what, that means what we have to prove, 8 raised to k plus 1 minus 3 raised to k plus 1 8 raised to k plus 1 minus 3 raised to k plus 1 is equal to 5 times some integers. That we want to prove. Okay, so we'll write this 8 raised to k plus 1. 8 raised to k plus 1 minus 3 raised to k plus 1 is equal to. Okay, so just you have to write this. Just I will write this what, 8 raised to k minus 3 raised to k here. Okay, so first I will write 8 now here. 8, right? I have managed this. 8 to the power k. Okay, so now this is not there. This is what I will write. This is what, plus 8 3 raised to k. 8 3 raised to k. So you want 5. Okay, so 8 3 raised to k. So you have only minus 1. You have only this. Okay, so plus I can write this as minus 3k plus 1 minus 3k plus 1. Okay, see here, if you simplify this, what we get, 8 raised to k plus 1 is there. Okay, minus 8 into 3 raised to k and plus 8 raised to 3 raised to k, it will get cancelled, right? And minus 3 raised to k plus 1, that means both the sides are now same. Now I can write 3 raised to k plus this. How can I write this is what, 8. I can write this is what 5m now. This is what I have written already this one. So what this is 8 raised to k minus 3 raised to k is 5m. I can write this is 5m now. No problem for this. 5m plus now this is what 8 3 raised to k minus 3 raised to k, because I can write 3 raised to k plus 1 as 3 raised to k into 3, that means 3 into 3. Now this is 8 3 raised to k and this is minus 3 raised to k, that means this is 8a minus 3a, so that is 5 now. Okay, so this is what 8 into 5m plus 5 into 3 raised to k, right? So now I can take the 5 common here, so I can take 5 common here. What do I get now here? 5 to the 8m. Now this is what 8m in plus now this is what into, so this is what 3 raised to k, right? Now your k is integer, your k is integer. Okay, here what for some k belongs to here, that means k is a natural number, right? K is natural number means it is an integer. 3 raised to k is also natural number. It is also integer. Your aim is what? Your aim is what? Integer. So 5m is integer. You know that the sum of the integer is integer, product of the integer is integer. So that means what here? So m is what here 8m. So I write here what 8m plus 3 raised to k belong to z. This is belong to z. That means what? 8 raised to k plus 1 minus 3 raised to k plus 1 is integral multiple of 5 now. This is what 5 into some integer, and I want to express this what in terms of 5, right? 5 into some integer. That means what? This is divisible by 5, or this is integral multiple of 5. So therefore 8 raised to k plus 1 minus 3 raised to k plus 1 is an integral multiple of integral multiple of 5, is an integral multiple of 5. So therefore pk plus 1 is true. pk plus 1 is true. So therefore by the principle of mathematical induction, by the principle of mathematical induction, Pn is true for all n belongs to n, right? So problem is over. Okay, so we'll take one more problem and then we'll stop. Okay. We'll take one more problem for n greater than 1. For n greater than 1. Prove that a set with n elements has 2 raised to n subsets. 2 raised to n subset. Okay. So with the help of the mathematical induction, you can prove this one. So I will give this as an exercise to you. Okay. So I hope that you can solve this with the help of the mathematical induction. Okay. So I think you understand how to solve the problem by using the mathematical induction. So what is here? Step 1 is very important. You have to assume that you have to suppose that the statement is here. Pn denotes the statement. Then second step is very important. That is what? Prove the result for n is equal to 1. So that means what? Put n is equal to 1. Take your LHS, RHS, right? And show that your LHS and RHS satisfy the given condition. They may or may not be equal. If you what? Less than or equal to, then that means what? Don't say LHS equal to RHS. So they satisfy the given conditions. Okay. So that we have to prove. Then what? The step 3 what? You have to assume that pk is true. So that means what? You have to write replace n by by k only. Okay, so don't do anything, write n as k only. Okay, now step 4 is what we want to prove, that pk plus 1. That is to prove that just replace n as k plus 1. Don't do anything. Okay, at least you can do this one. Okay, and try to prove the step 4, the step 4 now here. So that will be the help of the step 3. So take LHS, right? Do some calculations, or take step 3 and do calculations on step 3, so that you will get the step 4. Okay, so this is depend on the problem actually. We have solved the 5 problems on that, right? You will get idea how to solve the problems on the mathematical chain. Try to solve the problems in the exercise also, right? So purchase a book of this algebra from shopkeeper. So from the store. So which book you have to prove? You have to purchase. So this is the book. So this is written by myself and my friend. So that is what the golden series by Nirani Prakashan, algebra for semester 1, and the calculus is also there. Purchase both the books, so that you will get so many ideas about the subject and syllabus also. I hope that you understand this one. We will stop here. Thank you.